Hello, welcome to Maths with EJD. In this video, we are looking at the finite difference method for boundary value problems for ODEs. Generally, we know that ODEs can be divided into two types. We have the initial value problems and we have the boundary value problems. Okay. And for the boundary value problems, we have two methods for solving them. I mean, we have many methods for solving them, but we have considered two so far. We consider the Euler's method and the Runge-Kutta methods. Runge-Kutta, Runge-Kutta methods, especially of the fourth order. Then for the boundary value problems, now we're looking at finite difference method. And later we'll be looking at the shooting method. Okay. So, like I said, this is done. This is done. Now we are going for now we are going for the finite difference method, actually. So let's see how that goes. Um, finite difference. Finite difference method. So the first time we came across finite difference was when we we're talking about numerical differentiation. So we talked about finite difference and even operators for finite difference. So let's see how this works. The finite difference method, the finite difference method, if you like, FDM, is the finite difference method, or FDM, okay, is a numerical technique for solving a numerical technique for solving ordinary differential equations, especially when analytical solutions, when analytical solutions are difficult or impossible to obtain, or impossible to obtain. That's the whole essence of numerical analysis, right? So what is this about? It involves the FDM, finite difference method, involves discretizing the domain. We discretize the domain. We turn a continuous function into a discrete function. It involves discretizing the domain and approximating derivatives, approximating derivatives, derivatives, derivatives using difference formulas, using difference formulas. Finite difference method is especially useful for solving boundary value problems, where the solution, is subject, the solution is subject to boundary conditions at two or more points. Okay. Now, let's look at the general problem setup for finite difference method. General general problem setup. Okay, consider a general second order linear ordinary differential equation of the form d squared y dx squared equals f of x, y, and y prime, where x belongs to the closed interval AB, and we have boundary conditions that y at A equals alpha and y at B equals beta. Okay, so how do we go about it? This is the general so this is more like the general problem for boundary value problems. So as usual, these are the bound okay. So here you have this is the differential equation. This right here is a differential equation. And here you have your boundary condition. This is your boundary. This is your boundary condition, or these are your boundary conditions rather. And this is the domain. Okay. This is the domain for the definition for the problem. So having recognized those parts, how do you go about taking care of a problem like this? So see that the first step is to discretize. Discretization of the domain. Discretization of the domain. The domain is, of course, where x is defined for the problem. That's the closed interval AB. So you have to discretize that domain to turn that continuous function into a discrete function. So the first thing is you want to divide the interval. Divide the interval. So the domain, the domain, domain A, comma B is discretized. It is discretized into n equally spaced grid, grid points. Okay, the spacing between adjacent points is denoted as h, which is calculated as h equals b minus a divided by n. So that's how the discretization thing starts. So h equals b minus a divided by n. That's the first thing under the discretization. The second step under discretization would be to do the finite difference approximation. Okay, so you have the finite difference approximation. So, I mean, the whole idea of finite difference bears close resemblance with what we considered under numerical differentiation. Finite difference approximation. So, in the finite difference method, derivatives, like we already know, right? Derivatives are approximated. They are approximated by difference quotients. Difference quotients. So the second derivative, which is d squared y dx squared, is approximated using a central difference formula. A central difference formula at each interior grid point xi, so that we now have d squared y, the x squared is approximately yi plus 1 minus 2yi plus yi minus 1, this divided by h squared. So this is the finite difference equivalence of the second derivative, yi plus 1 minus 2yi plus yi minus 1 divided by h squared, which bears close resemblance with central difference that we considered under numerical differentiation. So that's the second step, or under discretization of the domain. So we have the third step. Step 3 for this will be to talk about the boundary conditions. Boundary conditions. Boundary conditions. So the boundary conditions y of A equals alpha and y of B equals beta are incorporated directly, into the system. Specifically, we know the values at the boundary points. So we have y naught to be alpha and yn to be beta. So this is y naught in the beginning and yn, which corresponds to what you have at the end. Okay. So with that settled, once you take care of the discretization process, we can go to the that's the second main step, apart from dividing the interval, right? And no, apart from discretization of the domain. So the next thing is to formulate the linear system. Okay. So formulating the linear system. So now you consider the second order linear ordinary differential equation, which is d squared y dx squared, and that is equal to f of x, y, y prime. And that has become yi plus 1 minus 2yi for central difference plus yi minus 1 all over h squared. That's square of the step size, all this over h squared, and that is equal to f of x, y, y prime, like that. So from here we can then we try to order this. So here we have so h squared can go to that side, as we know. So it's more like you're trying to, okay, this is what I should be having. We get rid of this. So this now is equal to f of xi, yi, yi prime. That's the idea there. So then we can cross multiply, right? So that we have yi plus 1 minus 2yi plus yi minus 1 equals, this is h squared actually. So h squared multiplied by f of xi, yi prime. Okay. So with all that, if we have a specific problem, okay, so far we have not been presented with a specific problem. So now we can reorganize this as this. So you have yi minus 1. That's a positive thing right there. And then you have minus 2 minus h squared. This comes minus 2 minus h squared f of xi, yi prime, like that. Then all of that, okay, this is 2yi. This is 2yi. So plus yi plus 1. So this yi, it's just, this like comes here so this comes to the back. It's like we are tucking this into this place. So this is coming like to the back, not to the other side. So the sign doesn't have to change. So this comes like this, and this comes like this. So sign is not changing for those. And all of this now is equal to 0. So if we rearrange all of this, yeah, I think it's safe to just leave it this way for now. So we have yi minus 1 minus 2. Okay, we can say this is minus 2 plus h squared minus 2yi plus h squared f of xi, yi prime plus yi plus 1 equals 0. So that's what we have so far. So of course, we need to be told what this expression is for us to know the next step we need to take. So if we assume, for instance, that our expression is f of xi, yi, okay, if we take it that expression, that we now have yi minus 1 minus 2yi plus h squared, and we take that expression on that one on the line to be, say, f of xi multiplied by yi, for instance. So we have this yi plus 1 equals 0. So it means we can rewrite that as yi minus 1 minus yi minus 1 minus 2 plus h squared multiplied by f of xi. Then you now have yi outside the bracket. So you see this yi and yi, we can collect them outside plus yi plus 1. So we can have this kind of expression in this situation. Okay, so that goes. Now with that down, let's look at a worked example. Say we have an example now. So to solve the boundary value problem, d squared y dx squared equals minus pi squared y, and all of that is for x lying between x starting from 0 to 1, okay? X starting from 0 to 1, and we have the boundary conditions that y of 0 is 0 and y of 1 is equal to 0 also, okay? So that's the problem we have. So can we go step after step to deal with that? So we go for step 1, like we learned already. Step 1 requires us to discretize the domain. Okay, we have the domain to be 0 to 1, clearly. So discretize the domain. So we divide the interval 0, the closed interval 0, comma 1 into n equals 5. So whatever we choose or whatever we're given, n equals 5 grid points. Grid points. So the grid spacing is h, which is 1 minus 0 all over 5. So that is 1 over 5, and that is 0 0.2. So we see that h is equal to 0 0.2. Good for the question. Then it means we are going to, that simply tells us that we are going to have x naught equals 0, x1 equals 0 0.2, x2 equals 0 0.4, x3 equals 0 0.6, x4 equals 0 0.8. And then we also have x5. So x5 equals 1.0. That's how that is going to be. So with all of that in place, now, the next thing we want to do is step 2. So for step 2, we now have this. Step 2, we apply the finite difference approximation. The finite difference approximation. So for that, see what we have using the central finite difference formula, for the second derivative, So we have yi plus 1 minus 2yi plus yi minus 1 all over h squared. And this is equal to minus pi squared y. This is our f of x, f of x, y, and y prime now. Just like what the question tells us. This is the question right here. Minus pi squared y. That's what we have right there. So we can rearrange this just like we did the other time. So let's go ahead and do the rearrangement. So now we have yi plus 1 minus 2yi, okay, plus yi minus 1 equals minus h squared pi squared y, like that. So we can, okay, of course, this has to be now yi, right? Yi, because we have brought it into that discretized form. So this is yi. So we can collect things together. So we have, so we bring yi minus 1 to the front, minus 2yi, okay, plus h squared pi squared yi. So this whole thing now is negative. So it comes to this other side and it becomes a positive, then plus, so this yi plus 1, all of this is now equal to 0. So we are doing this because we want what, but if we start from I equals 1, so this will easily be y naught. That's why we're bringing it forward. And this will be, so this yi plus 1 is going to be y2. So we want to arrange it in that order. So now we have yi minus 1 minus 2, all right, minus 2 plus h squared pi squared. Yi is common, so we have the yi out here. So when we take I to be 1, that's the least we can take. When I is 1, we have y1 minus 1, 0. So we have y1, and then this ends up with y2. So equals 0. So this becomes the expression we need to set up a linear system. Okay. So we try to use the finite difference system. But now we have values for h squared, pi squared, and blah blah. So imagine we already have h is 0 0.2. I think that's what we did h is 0 0.2 from what we did the other time. Pi, I mean, you want to take pi to be, say, 3.142 or something. So let's take pi to be 3.142. And then, of course, with this now, we can move on and say that this is actually yi minus 1, okay, minus 2 into 8 squared, that's 0.2 squared. Okay, that's minus 2, right, plus 0.2 squared into 3.142 squared, okay, and all of that into yi plus yi plus 1 equals 0. To be very sure about that calculation, let me check. So let me check 0.2 squared, 0.2 all squared, right? Okay, 0.2, 0.2 all raised to power 2, raised to power 2 multiplied by pi all raised to power 2 again. Okay, that's 0.3948 roughly. 0.3948. Okay, that's what that is. 0.3948. Okay. So we can just so we have yi minus 1 minus 2 plus 0.3948. That's what the whole of this gives us. Then yi plus yi plus 1 equals 0. Okay. So let me just continue with this now. So we have yi minus 1 minus 2.3948 yi plus yi plus 1 equals 0. So we have this system to contend with as we set up the linear system. So let's move on to talk about that. So step 3 now. Step 3, set up the linear system. So there's a linear system that can come out of this. Set up the linear system like we are required to. So this generates a whole matrix now. So what do we do? So when we take I to be equal to 0, okay? I mean, if I is 1, yeah? So at I equals 1, what happens? It means you're going to have y naught minus 2.3948 y1 plus y2 equals 0. That's just put 1 minus 1 0 1 here, 1 plus 1 2. So we have this system in this case. Then we go again at I equals 2 now. So we just have y1 minus 2.3948 y2, okay, plus y3, and that is also equal to 0. Okay, then so since we are going 5 steps, right? So since we are going to have 5 steps, so it means we have x naught to x5. So it means all we need is also y naught to y5. So once we get to 5, we stop. So we say at I equals 3, okay? At I equals 3, we have y2, that's 3 minus 1 here. 3 minus 1, that's 2. So y2 minus 2.3948 y3 plus y4, and that is equal to 0. Then we say at I equals 4 now. So it means 4 minus 1, that's y3 minus 2.3948 y4 plus y5 equals 0. So we know already, based on the step size we have, we go from x naught to x5. So it means we also need up to y5, and we have all of that here right now. So with this system in place, we can put this in matrix form. So in matrix form, we have generally AY equals B. And as you can see already, So from the boundary conditions, right, we have y of 0, like I said earlier, y of 0 is 0 and y of 1 is also 0. That automatically means that this is going to go to 0, y0 is going to be 0, and then y5 is also going to be 0. So at the end of the day, we are left with y1 to y4, and those are the things you're looking for. So the system now is going to be something like this. We have a now to be equal to minus 2.3948. That's, for this first system here, right? Y naught is already 0. So for y1, we have minus 2.398. Then y1 is 1, and every other thing is 0. So we have y1. I mean, y2 has a coefficient of 1. That's what I mean. Y2 here has a coefficient of 1. So then y3, y4 are all 0. So we have 0, 0. That is what A is going to end up being like. Let me give you some space because we'll need that later. So we have 1, 0, 0. Okay. Then next we have so here the coefficient of y1 is 1 and y2 is minus 2.3948. Then we have y3 and then y4 is 0. So here now we have this to be 1, then we have minus 2.3948 for y2, and y3 is 1, and then we have 0. Then we go for the third one where the third one where I is 3. So we see that y2, the coefficient of y2 is 1, and the coefficient of y3 is minus 2.3948, and y4 is 1. So it means that y1 alone is going to be 0 in this situation. So we have 0 for y1, then 1 for y2, minus 2.3948, which happens to be the diagonal. And then now y4 in this case would be, this is 0, 1, yeah, would be 1. Okay, 1, 2, 3, 4. Yeah, that would be 1. And lastly, for I equals 4, y3 is 1, y4 is minus 2.3948, and every other thing is actually 0. Okay, so this is y3 is 1, right? So we have 0, 0, y3 is 1, and lastly y4 with minus 2.3948. So you see that 2.39 minus 2.3948 coming along the principal diagonal all the way. So that is our A. Then of course y, as you can already imagine, the y will be solving will be all so we'll be solving y equals y1, y2, y3, y4. Since we already know y naught and y5, we already know that y naught is equal to y5 is equal to 0. Those are the boundary conditions that we already have. Then, of course, the b, that's the right-hand side now. The b now is simply 0 all the way, 1, 2, 3, 4. That's what our b is going to look like. So that's the linear system from what we have. That's the linear system. So with that taken care of, so we can go for step 4. So in step 4, we solve the system. Solve the system. Of course, I have a whole playlist on matrix, and we've done things relating to matrix a lot of times. So we need that idea here, which I'm not going to bother about because I'm just going to show how the Python does it. So the matrix system can be solved using methods such as Gaussian elimination. Thankfully, the matrix is maybe some kind of sparse. So such as Gaussian elimination. Okay, elimination, LU decomposition, or by using iterative methods. Thankfully, I've done all of this also under this playlist. I've done all of these methods, iterative methods like Gauss-Seidel, Jacobi, and all that. So, once the system is solved, for y1, y2, y3, and y4, since we know y naught and y5 already, then we can obtain we can obtain the approximations. We can obtain the approximations of the solution at the interior points. At the interior points. Okay. So another step we want to take is step 5, where we compare the numerical solution with the exact solution. So compare with exact solution. Compare with exact solution. Of course, when this problem is solved, right, the exact solution to the differential equation, is y of x equals sine of pi x. That's the exact solution. Okay, so with this now we can see how effective our method is. So by evaluating this at the grid points, so the grid points, of course, will be x1, x2, x3, and x4. So by evaluating it at this point, we can compare the numerical solution with the exact solution. All right, so for n equals 5, which we have, for n equals 5, the computed values of y1, y2, y3, and y4 will be very close, to the exact values, of yx, which is equal to sine pi x at the corresponding points. Okay. Now, I mean, that matrix, the way it's set up already, we can solve it using any of the methods, and we can also use computation, which I'm going to focus on. So this is a matrix here, and we just need to solve for y1 to y4. And because that can be a bit time consuming, so I'll just go for the Python implementation as we have right here. So if you look at this now, this is the Python implementation. You see in line 5, we have the left boundary, and line 6, we have the right boundary. That's y of 0 equals 0 and y of 1 equals 0. So those are then n is 5, the number of subintervals which we used, and then we have the grid space in which is h equals b minus a over n. Then the exact solution, we have it here. That's sine pi x. Actually, yeah, the exact solution we have is that's sine pi of x. This is the right hand side of the problem itself, which is minus pi squared and all that. So now we define the matrix A for system of equations. So that matrix that led us to that expression that gave us the matrix, this is what you have here. That's minus 2 minus h squared pi squared and all that. That's all of that here in line 20. Then you have the matrix itself. I've done it in such a way that the matrix will be outputed, so you can see that it's the same matrix that was generated up there. Then you define the boundary conditions that y of 0 is 0, just like we have in the question, and then you compute the right hand side vector. I think that's the source term evaluated at interior points. You have all that. Then you can study this. Just check on Facebook. You find it there. I'm not able to put it on YouTube for some reason. I mean, I think because of the some special brackets that you have in the code. So if I run this, we can see what it looks like. So you can see the that principal diagonal is there. You have the minus 0.3948 and all that. Then you have all the other values like that. So you see the values now. So for the steps now, starting from 0 to 1.0, you have all that. And the numerical values, you have 0.00, and down, of course, it starts with 0 and ends with 0, but in between you have 298. So it means that y1 numerically is 2948743, Y2 is 483376. Y3 is 4837 0.483376. That is. Y4 is 0.298743. Okay. And these are the exact solutions. So you see the errors as they go. So, and of course, we can also visualize. So you see the blue is the numerical solution. The exact solution is the one in orange. So the error itself is shown in red right here. So you can actually use finite difference method like that to deal with boundary value problems. It can be a bit tedious, but I mean, it's not impossible to deal with. So that helps a bit. Now, in conclusion, right? Of course, you want to study the code. I think the code, once we begin to get to all these boundary value problems, they can be quite complicated. Um, so you want to really, so at this point, coding becomes very useful like that. So that is important to pay attention to. Of course, so we see already that for boundary value problems, like we have seen so far, the finite difference method uh, provides a simple, powerful tool for boundary value problems of ordinary differential equations. Then by discretizing the domain and approximating the derivatives, the method transforms the differential equation into a system of algebraic equations, which can then be solved numerically. And this method is particularly useful for problems that are difficult or impossible to solve analytically. Okay, so let's take some practice questions as we end this. Practice questions. So you want to try your hands on it. Try to follow the steps, do all the discretization before you end up with the Python code. So let me see. Solve solve the BVP using finite difference method with n equals 5 grid points. N equals 5 grid points. So what's the BVP? It's d squared y dx squared equals minus y. Then 0 is less than or equal to x is less than or equal to 1. And then the boundary condition is y of 0 equals 0 and y of 1 equals 0 also. That's the first question. Then we can have a question 2. Question 2, consider the BVP. Consider the BVP, d squared y dx squared equals x squared plus y. Define within the same 0 less than or equal to x less than or equal to 1. And of course, y of 0 equals 0. Y of 1 equals 1. So in this case, y of 1 is not 0. So you're going to have, depending on what intervals you're going to have. So you may have to choose your own grid points here as you like. So because it's not specified, then we have question 3. Solve the BVP using finite difference method, of course. That's d squared y dx squared equals 2x plus 3, 2y plus 3x, 2y plus 3x, 0 less than or equal to x less than or equal to 2. Then, of course, y of 0 is 0 and y of 2 is equal to 4. So you discover that the boundaries are at the beginning and the end of the interval as usual. Okay, so the steps that are not been given, so you have to choose your own. Then if we have a fourth question, question 4, right? Question 4, solve the BVP, solve the boundary value problem, d squared y dx squared equals 4x minus 2y on the interval 0 less than or equal to x less than or equal to 1. Then y of 0 is 1, y of 1 is equal to 3. And lastly, we have a fifth one, question 5. Consider d squared y dx squared, which is equal to e raised to power x, where you have 0 less than or equal to x less than or equal to 1. And of course, the boundaries, y of 0 is 1 and y of 1 is equal to 2. Then solve using finite difference method. So, I mean, this provides ample opportunity for you to try your hands using finite difference method on boundary value problems. So this is question 1, question 2 in green, question 3, question 4, and question 5. So let me see your answers in the comment section as much as possible. Then, of course, let me also know how helpful these videos are. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. If you have subscribed, thank you. If you have not, please go ahead and do that and hit the notification bell so you can always get alerted each time a new video is released. All right. Don't forget to also share, like and share so that more people can have access to this great learning. In the next video, I'll be talking about the shooting method, which is another method for solving boundary value problems. So watch out for that. Till I come your way again, keep doing maths right. Bye.